Hey everybody. Before we begin going into all sorts of, actual coding stuff, just wanted to kind of talk about computer programming in general. So, brief history lesson on computers and sort of where computer programming comes from. The first, I'm going to say commercially available, but let's be honest, like if you weren't a government agency or a very large corporation, there was no way you could afford one. The military was a big purchaser, right? But the first sort of commercially available general purpose computer was the ENIAC. The ENIAC, to be programmed, had to use machine code. It's actually what you see these people doing by actually plugging wires into sockets, right? Like that is actually how we programmed our sort of ones and zeros, each byte, sort of physically in the computer. Things got a lot better as time went on, of course. This is actually the first personal computer, the Altair. Came out in 1975, would be quickly followed by the Apple II a few years later. In fact, I think the Apple I was the very next year, and Apple II was a couple years after that. But regardless, this was sort of the first personal computer. Believe it or not, it was incredibly popular for its time. It also made Microsoft an actual company when they developed the basic programming language for it. But originally, it was exactly what you see right now, a box of switches. Each of those switches was a 1 or a 0. And so you could flip switches in order to, make a program. If you wanted to add, 2 plus 3, you would flip a series of switches for the plus, a series of switches for the 2, a series of switches for the 3, and if first and third lights turned on, that was 5, right? You had to know binary, and you had to sort of do everything by hand. Point being, all computers at their core have to be given instructions in machine code. There's no other way to get around it. All programming leads to that. So what is machine code? Your computer processor is sort of broken up into 3 sort of big parts. It's actually a lot more now. It's more complicated, but regardless, we'll get rid of caches and things like that that are just sort of ways of optimizing. There is a control unit that sort of controls the flow of sort of the order of going through a program. What's the next line of code I'm going to execute, etc. The ALU is sort of a series of circuits that each do specific operations. And so if I send, let's say, 2 signals down these particular pathways, maybe those 2 signals represent numbers, and then at the end of the pathway, those numbers will be added together. That would be like the add pathway in the ALU. But there's lots of others like shift and stuff that we probably don't use as often. Early computers didn't actually have stuff for multiplication. Multiplication was done by sending numbers repeatedly through the addition circuit. Division can be done with, actually subtraction can be done by simply flipping the sign of one of the numbers and then running it through the addition circuit. There's lots of different little tricks that people have done over the years to be optimal. But now we have multiplication and all sorts of stuff. Point being, the ALU are sort of a set of circuits that you have to send information through in order to perform an operation. The registers are just memory. In fact, they're the fastest memory on your computer. They are the closest to the ALU, closest to the center of the sort of CPU. And to send something through the ALU, it has to be loaded into a register first. And so that's kind of the way your CPU is set up. So here is what a machine instruction might look like if you shortened it so that it would fit onto a slide. You've got, and by the way, there's lots of different machines that take different types of machine instructions. This is just an example of one that might exist, and I think it's very similar to the Intel one. So you start with a portion of your instruction that is the instruction opcode. That could be to load from memory, it could be to store somewhere, it could be to do any number of things. That instruction opcode has a binary sort of number associated with it. And so you could look through the instruction set of any particular processor, and all of the different instructions you have available to you would have a different instruction opcode for addition, whatever. The second is the location, the register location, because it has to be in a register, of your first input. I'll call it input A. Some instructions may only have one input, by the way. That's fine. But, sort of unary, operators. But Others will have a second one, so that's what the green portion is, B, right? That's your second input, your second register location. Now you have to put the answer somewhere. An answer is going to go back into a register, but instead of putting a third set of instructions, since we've already used A and B, we could just use A as the place where we send the answer as well. This is an example of a way you might design a machine instruction. It's very common, but point being, others may be slightly different. But you're getting the kind of idea. This is one instruction, but it's all in ones and zeros. It's all in those individual switches being flipped, at bytes, in order to create this one instruction. Now, at some point, somebody realized it would be a lot easier if we could somehow convert that into something that we could type and it would be a little bit more readable. I say a little bit more readable, but here is assembly language. So assembly language has like a one-to-one relationship with machine code. I don't believe there's any optimization that happens after assembly, but I could be wrong there. There may be some optimization code that gets run. In modern systems, optimizations are run at multiple different locations, but let's assume for right now, like in the old days, there's a one-to-one relationship. So the functions load, multiply, and store all have particular instruction opcodes for that particular instruction set, and like they are set. So if it's load, I just have to convert that to 1011011111, whatever the heck it is, right? So it's very easy to sort of go from assembly into machine code because everything is sort of set. Your registers would not be called registers 1 and registers 2. They have really weird like EAX names and stuff like that, but I'm simplifying things because you don't really need to know any of that yet. There'll be a computer architecture class at some point in your future, I'm sure. But now you can kind of see what we're doing, right? I'm going to load into register 1 whatever is in location, whatever memory location 1024. And then I'm going to load into register 2 whatever's in memory location 1028. Then I'm going to multiply whatever's in register 1 by whatever's in register 2, take the answer, put that back into register 1. Then I'm going to store whatever in register 1 into memory location 1020. It took me 4 lines of assembly code in order to just multiply 2 numbers together. Assembly is hard to write in. It's very detailed to write in. How about we go with that kind of language? So then, how do you get from assembly code to machine code? You use a compiler. Technically, that's not true. You use an assembler. You can see that they're on the screen there. But, if you say compiler, I at least know a lot of people who are working programmers who would be perfectly okay with you saying that. Every once in a while, like we'll talk, the difference between what is an argument and a parameter. They are actually different, but if you just say parameter for everything, usually people are okay in common conversation. Regardless, you use something that's going to convert from one language to another. It happens to be called an assembler. So, if you have these programs that can convert from one language to another, right? They can convert assembly into machine language. Then why wouldn't you create another, and by the way, machine code is nearly impossible to write code in. I mean, I couldn't imagine writing a website in machine code, right? Assembly code is really hard to write code in, although not impossible. And if you're an engineering major, a lot of PLC controllers and stuff like that actually are written in assembly language, right? But you're doing really simple things where it's just like, based on the input from this sensor, I want to move this actuator, a percentage of that amount or whatever. So it's usually very simple things you're doing in assembly. It's unlikely you're going to develop a video game in assembly, right? So if that's possible, then why not use a compiler to use a higher level language, something that's closer to English, and then convert that into assembly and then convert that into machine language? That seems like a perfectly reasonable thing to do. Like, that's what we do. In fact, at this point, you might actually be asking, why don't we just create a compiler that can convert from English into C++? Then life would be so much easier. The problem is that English is an incredibly ambiguous language. And even if we were to do it, the kind of English that you would have to speak or type in order to get it to convert to C++ and actually get what the intention you're meaning would still look like code anyway. The closest example of that would be like lawyers kind of have this like lawyer speak that they use. And it's because, and by the way, even that lawyer speak can be incredibly ambiguous, and that's why we have courts and decisions and all sorts of history that lawyers have to learn. It's because even that's an imprecise language, but it's at least a lot more precise than standard English. So, yeah, maybe there's some sort of like uber lawyer speak we could create, but if we did, it would be just as complicated as code. So, low-level languages, like assembly, tend to focus on hardware operations and solutions that are sort of unique to a specific platform. And even, again, in engineering, you'll see applications for it. Whereas higher-level languages allow us to sort of get rid of those implementations. I don't need to know, if I want to multiply two numbers together, I can just say, I want to multiply this number by 3, right? Like literally it could be 3 little tokens, a variable name, or even just a regular number, right? And then a multiplication operator, and then another number, and now I've multiplied these two numbers together. I can think at a higher level, and I don't have to worry about the underlying implementation of how I actually have to do that in assembly, or how to actually get that to work in machine language, which is obviously helpful if you're wanting to write a video game. Higher level languages were invented I shouldn't say invented, they were sort of brought closer to English in 1959 by Rear Admiral Grace Hopper with the first sort of English-like computer language COBOL. The reason I say that is because Fortran technically precedes COBOL, but COBOL is sort of the first more English-like one. Fortran was very sort of math calculatory in its implementation. But regardless, by the way, she also, you can see the note there for yourself, but she invented the term debugging when she was working at the Mark II computer at Harvard, and a moth flew into the relay panel, and she went and found it, pulled it out, and I believe taped it into the log for that system and said, I found a bug in the system. And ever since, we've called them bugs. Anyway, so compilers also allow you to do one other thing. Again, not strictly the compiler. It's the linker and loader, but whatever. It allows you to link and load common libraries of code that's already been written, right? If you do want to go out and do something more complicated, like create a mobile app, right? There's a ton of code out there that's already written for you to get your ideas onto that screen. You don't want to have to go back and start from ground zero. How do I generate a window? How do I generate, no, you can just, work on the stuff that's unique to what you're creating, your solution, and use libraries of code that's already written to, help you out there. And thank goodness, because if I ever had to write a, computer game, or if I wanted to make a computer game, the pure math behind the fluid dynamics of you just walking through water and having the light reflect off of that water. I couldn't do that. I can't do that right now. I would take me months of research to be able to do that. And when I say months, I am being incredibly generous to myself. I mean, I'm sure the person who originally came up with it probably took them years, and I just, probably got a PhD for it along the way. And here I am. I'm just trying to copy what they did, and it would probably still take me years. That code's already written. It's so much easier to just say, I need a fluid, I want it here, I want it at this opacity, I want it at this viscosity, right? You can reuse stuff. Now, for this class, we're doing very simple things. So for the most part, we're going to be just sending stuff to the screen. But even then, without, sort of those libraries, it would be very complicated to just get, pixels to light up on a screen. Because we have those libraries and those standard ways of doing things, it's a lot easier. So yeah, loaders and linkers help out a lot. You don't want to reinvent the wheel. Some libraries are really big, and you probably know about them because you have to update them every once in a while, like DirectX. Some are about interacting with the operating system, like WinRT. If you're a mobile situation, right, you're probably dealing with Cocoa Touch for iOS, or anything in the Android sort of OS. There's all of this code that's already written, and often you're just trying to interact with them. So here is the overall diagram of what happens. You have your C++ source code. That source code is run through a preprocessor, which I didn't mention that process, but we will later on. It goes through the preprocessor and becomes modified C++ source code. That preprocessor just kind of goes in, it does some like find and replace stuff, and basically just changes it. So it's still like a text file. It's just a text file that's had all these changes made based on some things you threw in. Also tells like what you want to load and link at the end. Then we go through the compiler. The compiler will move us from the modified C++ source code to assembly code. Right? The assembly code then goes through the assembler to become machine code. At that point, the loader and linker hooks it up with other library code, and at the end of the day, you get this little thing on your screen that you can double click and it will run your program, the executable binary. This is the little thing that people want to install onto their computer so that they can use your software, or download from the Google Play Store so that they can run it on their Android device, whatever it happens to be. Right? This is the thing that has some value, right? And it may not be much, right? It may be an app that you sell for 99 cents that plays a game that kids would like. Awesome, right? Like, would I spend 99 cents to keep my kid entertained? I'm saying 99 cents. Boy, I'm dating myself. Would I spend $2.99, $5.99? Would I download it for free and spend $180 in like online currency over the course of the next 6 months? Just the way most video games work these days. Maybe, right? That thing has a value. And the nice thing is that thing can be copied millions of times, like within seconds, and downloaded and distributed to other people. And it costs you nothing to create more of them, right? Like anything in the physical world, like if you made shoes for a living, and you made a great pair of shoes, and people are like, "Oh man, I like those pair of shoes. Can you get me a copy of those shoes?" It'd be like, "Sure." It'll take 2 weeks, and I've got to like buy some leather and take some time, and there's material cost, and there's no cost for these copies, right? Like once you create it, that idea that you had, you knew this special language, you wrote it, it becomes this executable binary, and that's sort of where you fit in, right? You are the programmer. You use a text editor to create that C++ source file in that special magic language that then ends up becoming this executable binary that maybe has a value. And so that's kind of the goal of computer programming, and what we're doing is creating value out of ideas, right? You have an idea, something you think is great, and we want to give you those skills that you need to be able to actually create something that you can produce from it. Even if it's just virtual. By the way, having great ideas, a lot harder than it sounds. Half the people who come up to me and say like, "Oh, I've got this great idea for an app, blah, 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 blah," and I'm just like, Facebook. You're describing Facebook. Facebook already does that, whatever. So yeah, you get the idea. The language that we're particularly learning here is C++. C++ was created by Bjorn Stroustrup. I am 70% sure I'm pronouncing that right, because I believe I've heard it before many times, but even then, Bjorn Stroustrup at Bell Labs, which is a very famous place. It's where C was actually developed by Dennis Ritchie, in 1969. And so it's in the early 80s. His goal was to make programming easier, which is going to sound laughable to anybody who's ever studied C++, because it's now considered one of the more difficult languages, but at the time, it was actually making things easier. This new paradigm of programming had popped up called object-oriented programming. And so he wanted to add tools to add object-oriented programming to C++, but to not be solely object-oriented. You could still do functional programming. You could still do what we call structured programming. Later on, the ability to do sort of more abstract programming came out. But the idea is that he was trying to base it on the needs of people who were actually making programs. The practical was considered more important than the theoretical. And so that's one of the reasons why C++ became so popular. It was a great tool for creating particularly system software, because you can get to really low levels, function pointers, and just the ability to use memory with pointers to begin with, right, to create your own data structures. There's a reason why most operating systems to this day are still written in C or C++. That language has, a place still. And also a lot of web programming is C or C++. Or no, sorry, not web programming. Video game programming. Web programming is a whole other story. When you're connected by a wire that's really slow, being a fast compiled language with really low level access to hardware really doesn't do you a whole lot of good. It's still going to have to go across a wire, and that's going to be incredibly slow. So let's talk about sort of the traditional first program and kind of dissect it in C++. The Hello World program. We are going to do ours in CLion. I happen to already have CLion loaded up and ready to go. This is the welcome screen for CLion. Now, hopefully you were able to get it installed already and put into your system. There's lots of other IDEs out there. They all kind of work similarly. This is one where the Mac version and the PC version are very, very similar. It also happens to have some really nice features that I like. So, you know, it's a good choice, but not the only choice by far. And some people prefer not to have a full IDE. Some people prefer to just have a low, sort of much more streamlined text editor and do a lot of stuff in command line. That is also a great solution. It's just not the solution I'm suggesting, especially for a beginner. So if you're using CLion, we want to create a new project. I'm not going to insult your intelligence. There is a new project button right there. So just click it. This is going to be where you sort of can make some choices here. We are going to create a C++ executable. We're trying to create a program, not a library of code. Here I get to select the version of C++ that I want. I'm going to go ahead and choose the new version, because why not? The new version will generally support all the old version stuff. You just get access to new stuff, but really it doesn't matter. If you left it on C++ 14, that's okay. We're not going to use any of those new features. I don't think 18 weeks is enough for us to get to closures. I'm utterly shocked that we can get to like subclassing and like polymorphism. That's about as much as I want to cram into one class. So here we go. So I'm going to choose my version here. And then here you'll notice the location. This is not my favorite. I wish you could name the project separately, but instead what you get is sort of the path to your project folder. And at this point, untitled is the name of my project. I don't want that. I'm going to call my project something else. I'm going to call it, let's say, Hello, since Hello World is the traditional first program in, computer science classes. But by the way, notice that this is also the location of that project folder. That project folder is going to become important, right, over time. So, because that's where I need to go to find my executable as well as my source code so that I can submit it to Canvas. So down here I'm going to hit create, and it is going to load a project. Now this is going to take a second. In fact, you may think like, oh hey, look, I can do stuff now. You can't really. Look down here, it says loading CMake project. So when you're in a big IDE, and this will be probably a negative of IDEs, it's kind of like stepping into the cockpit of a very large aircraft. There are lots of bells and whistles, lots of buttons, lots of switches. What do they all do? And it's like, they're all there to help you collaborate with others, to help you to do all sorts of stuff. But like when you're first beginning and all you're doing is learning how to like taxi the airplane on the runway, you have a throttle that gives you some thrust and two pedals on the floor to steer. Which if you didn't know, that's how you steer a plane when it's on the ground. Now you know. There's two pedals on the floor, right? That's how you steer a plane. Don't touch any other bells and whistles. They're there. You don't know what they're there for, so don't touch them, right? Just trust the system for a little bit, and over time you'll learn more and more about each little section, and that's great. Right now, it is, you can see down here, it says updating symbols. Yeah, it's updating symbols. So let it do its thing. I'm not even going to bother. I could actually start talking, but in general, it's good practice to let it do its part. Hopefully you can hear me over the fans. I will say this is the other problem with IDEs, is that they tend to be a little bit power hungry. If you try running multiple at the same time, you'll know what I'm talking about. So over here in the left panel, you'll see your project folder as well as its contents. Here I've got a file called cmakelists.txt. It's also right here in my editor, which is sort of the right side where I can actually edit stuff. And by the way, my font is huge so that you can see it, right? But so here's the thing. This sort of tells us like what files we want to all execute together and what we want the name of the executable to be. We don't need to worry about that. So I'm just going to close that tab so you won't be tempted to touch it. It's fine for right now, okay? We'll just call it voodoo. Anything I don't know in computer science, I call it voodoo. Some people call them black boxes, whatever. I just like, listen, I do this, and at that point it's voodoo. And that may seem like it's lazy, but trust me, at some point there will be some level at which you will have to accept that you don't know how the voodoo works. Somebody else who works at a different company, who's either higher in abstraction than you or lower in abstraction than you, and we'll talk about abstraction later, but like somebody understands how that voodoo works, but you just need to know how your voodoo works. So, because it's not voodoo to you. So here we go. Here's our main CPP file. Now it's obviously already opened in the editor, but if I wanted to, I could click it there. I would see it then opened here. And well, sure enough, boy, C-Line, such a helpful thing. It's already written your first program for you. Because Hello World is such a common thing that, you know, they've even gone to the extreme of putting in that comma for you, which makes this correct English, because hello is whatever that clause is at the front of a sentence that I don't know because I don't teach English, but anyway, it doesn't just say hello world, it actually says hello world in correct English. So let's talk about what some of these bits are. First thing we want to talk about is your preprocessor directives. So anything that begins with a hashtag like this, in C++ at least, is a preprocessor directive. It means you're telling the preprocessor to do something. In this case, we're telling it to include something. We're telling it to include IOStream. Now, IOStream is a library that is very famous, right? It's part of the standard C++ package, and it has lots of objects and functions in it that we can use to get stuff to, well, it stands for input-output streams. Basically, to use streams to send stuff to the screen, get stuff from the keyboard, move stuff around a bit. Not to files, that would be fstream. We'll include that library in a later project. But for right now, IOStream is sufficient for us. We're just trying to get the words hello world to the screen. Now, there's often something that I put here on the second line. And if you look at my slides or something, you'll see it. I'm going to wait for a second. We'll get back to it later because I will talk about namespaces, but not yet. And so then here we have sort of the main part of our program. In fact, it's so main, we call it main. This is our function, the only function in our program. This function happens to have a special name. The name is called main. Main is only important because, well, in like a lot of different languages, main is the first function that gets called when your executable is run. So that, if you double-click the icon to run your program, it's going to go to main, and you're going to execute that code. That's true across many things, even in like newer languages like Apple's Swift language. Every time you hit one of those little icons on your iPhone, it calls a function called main. Now, main is kind of hidden by Apple. You got to look to find it. But when you do find it, you find out that it's just one line of code that calls a different function that Apple wrote also. So it doesn't really do a whole lot other than get the process started. But that's why it's called main. You can't call it anything else. If you called it anything else, you wouldn't have a main program, and your computer wouldn't know what to do when you double-click on that icon. So this function has two basic parts. The header that I'm highlighting now, which gives us some basic information as well as the name of the function, and the body. Oh no, don't move stuff. Bad me, bad me. All right, here's the body. The body is essentially all the lines of code that we are going to execute when we run our program. Now you'll notice it is delimited. That's a very fancy word for it's sort of boxed in or, contained by these little things that I'm going to call curly braces. I don't have to call them curly braces. That's kind of like calling cows moo cows. The adjective here is completely redundant. All braces are curly, by the way. That is a brace. That is a bracket, and that is a parentheses. They all have different meanings in C++, so you have to use the right one. Anyway, curly braces are going to delimit blocks of code. And so we're going to say that this block of code is our main function. It's going to contain several lines that do stuff. So now let's start with the header, because it's going to be sort of the part that tells us some stuff. Now, we are going to go over a lot of this information again when we start writing our own custom functions. Here, I'm really just trying to give you sort of like, I don't know, some background so that when you're looking at stuff, you don't think like, oh, I have no idea what that is. Like, I feel so lost because I don't know what anything is. It's like, no, this is just part of it, and we'll have multiple functions later on. In fact, we'll have multiple files that each contain multiple functions that are all probably contained within classes, that yada yada. We'll have more, right? But like right now, just looking at this one, the function is called main. And sometimes if we're writing stuff in English, we'll actually write the function name with those parentheses there. I'm not in Canvas, so I can just do it like that. But like, we'll say that that is the name, the main. And the reason we put those parentheses there is because for functions, there's always parentheses after the name. And that kind of tells us that that is not a variable, which we'll talk about next week, but that is a function. So, and we'll talk about why I did the slash in some other day. Actually, no, we'll talk about it later today. And so here, I've got a function called main. It's got a sort of set of parentheses here with nothing inside of it. That seems a little suspicious. And the word int in front of the main. So what is this all about? Functions can actually take input and provide output. They do something, right? And you can send information to a function. They can process that information, and when it's done, it will then give you back some sort of result. Well, C++ is a strictly typed language. So for everything that's moving in and out, I need to know what type it is. We'll talk about types next week when we talk about variables, but I'll at least tell you two today. One is strictly not a native type. It's actually kind of more of an object, but yeah, we'll be fine. The first one is called an int. So an int is just an integer, right? A counting number. 1, 2, 3, 4, -3, 0, right? Those are all integers. There's a decimal point in it, not an integer, right? That's something else. We'll talk about next week. But for right now, this function is going to return an integer, right? The type of the function is integer. So I know that whenever this function is executed, it is going to return to me, if I make a call to main, and you will never make a call to main, the system will make a call to main, right? But you will not. But if I were to make a call to main, let's say that I'm the operating system, I make a call to main, I should expect to get an integer back, right? That's the advantage of main, right? That's what I expect to get back from main. Now, what do I need to provide main in order to get that? Well, the answer is absolutely nothing, right? And that's why that's empty. Now, by the way, depending on your IDE, you might see this, the word void. The word void just means nothing. So it's kind of the exact same thing. But you don't have to put the word void there. You can leave it out. This is one of the unfortunate things about C++. It seems like it's positive until you're learning a language, and then you realize that having 50 different ways of doing any one thing is actually harder to learn. But these do the exact same things. Now, you might even see a bunch of gobbledygook, and I'm not even going to explain it right now, but that's because in the days of command line programming, you used to actually be able to send like input into a program. For instance, I'm going to go off the rails. Why am I doing this? Don't do it, don't do it, don't do it. I'm going to do it anyway. Can't stop me. Okay, so, that's right. Apple changed their default shell. It's fine. Don't worry about it. So here I am. I'm in my terminal prompt back in, 1981. Bon Jovi. Actually, no, Bon Jovi wasn't popular until later in the 80s. It's fine. Regardless, you can picture the 80s. I'm here working on a terminal, and I need to use a program. So let's say I want to use a program that will at least tell me what's in my current folder. Just know that I'm in my home folder right now, as much as you can be in anything in command line. And so I am going to try to list everything that's there. I will do that with ls. So ls will tell me everything that's in there, right? These are all of the different folders and, files that happen to be in my home directory. Okay, great. But I could also send input to that program. So I could type, for instance, ls -l. Now that is sometimes called a switch, but it's a way of sending input to the ls program to say, hey, by the way, when you list everything out, I want you to list it in long form. What's long form? Long form tells me all of the permissions, who owns, what part of what group, when was the last time it was edited, as well as the name of all of the different directories and files in my home folder, right? So you can see all that stuff there. Like it's, a lot, but it's a way of providing input to that program. We are not going to worry about that. So you can just leave yours blank. If you have a bunch of gobbledygook in there, which basically tells you, it gives you an array of all of the inputs that came in, as well as the number of inputs that came in so that you can traverse the array. But none of that's going to make sense to you right now. So we're going to call it gobbledygook, and it's gone, and you don't need it. You can just erase it if you want to. If you leave it there, it's fine. But if you're using CLion, like I recommended, then it wasn't there to begin with, and so you're okay. But this is where we could provide input to a function so that it could use that input to do its job. Now, we get to the body, the actual lines of code that are going to be executed. So let's look at the body of this function implementation. By the way, we would call this entire thing. Some books will call it a function definition. Some people will call it a function implementation. I tend to bounce back and forth, honestly. But I try to say implementation more often because I think that's the more popular term nowadays. So here I've got the lines of code inside of here that I want to execute, including the one line of code in all of this program that actually does anything. And by the way, if this class were in Python or in Swift or any sort of modern language, your first program would look like this. Yeah, so much easier. One line of code, and it happens to be the one line of code that actually does something. But in C++, everything must be inside a function. I shouldn't say everything should be inside a function. There's globals and stuff like that. But because execution starts with a function, your code needs to sort of start in that function. So this is the one line of code that does something. It's got several parts to it. The first is this thing right here, standard cout. So what is standard cout? Cout is just an object. It's something that's used as part of streams. It comes in that IOStream library. That's why we can use it. If I were to get rid of this line, you would notice that suddenly, hey, wait, it doesn't know what these two things are over here. It's because I just got rid of including the library that cout was a part of. So I will go back to that. So what does cout do? Cout sends stuff to the screen, like to the terminal window. So cout, picture it like a little wormhole. And anything I send to that wormhole is going to get sent through and appear on the terminal window or on the screen, right? You can see where the output goes in CLion when we actually run this. And so that's what cout does. These little arrows that sort of point toward the cout, that's because I'm wanting to send stuff in the stream to that object so that it can go through the wormhole and appear on the screen, right? What can I send? I could send variables, different, larger expressions of different things. I could send the output of functions to the screen. I could send lots of stuff. But what am I choosing to send to the screen in this particular case? I am sending a string, which will be the second type of thing that we learn, even though it's not a native primitive type. Well, C-style strings kind of are, but they're just an array of characters. But here's the thing. It is a string of characters, right? A bunch of characters, letters, numbers, symbols, anything that's in the ASCII library, and in fact, some stuff that's not in the ASCII library, we'll talk about that in a second, that I want to have appear on screen, I can do that by sending this string, right? The string is also delimited, using that fancy word again. It's sort of boxed in or contained by quotes. So anything inside these quotes is going to be sent to the string, or be sent to the cout. It's part of the string. The quotes themselves are not part of the string. And so when we print this out, we're not going to see quote hello world. We're just going to see hello world, the stuff that's inside the quotes. If it's inside the quotes, it's part of the string. If it's outside the quotes, it's not part of the string. And so I want to send one thing to the cout. My one thing is a string of characters that starts with an exclamation point. It starts with a quote and ends with a quote. And the contents is hello, comma, world, exclamation point. All right. Then I want to send one other thing. The one other thing I want to send is standard inline. So what's this? This is an object that basically represents you hitting return or enter on your keyboard in Word. It just drops the cursor that we're printing stuff down and to the left so we can start a new line. That's it. There's actually other ways of doing that too, because this is C++. 50 different ways to do anything. There's probably a Paul Simon tie-in with like 50 ways to lose your lever or something, but I'm not going to go there. Regardless, that just ends the line. So then, the last thing we do is we return 0. We've already sent this to the screen. We want to end our program, and so we do that by returning 0. Now, why do we return 0? We return 0 because back in the day, that was the way you said, execution is halted, but everything's okay. There you go. Execution is halted, but everything's okay. Like, I meant to do that, right? It's like, I slipped and fell, but like, I meant to do that. It's okay, I'm good. Like, that was actually the intended, I was, wanting to. Return 0 means everything was okay. Presumably, you could return other things and it would not be okay, and those codes could possibly be interpreted by whatever, but we don't really use those anymore. And so, in later versions of C++, they actually said you can actually eliminate that line. This will run just fine. And when I do, by the way, I ran that by pressing the little run button up here. And you can see it executed some code, and at the end of the day said, hello world. Process finished with exit code 0, even though I never put return 0 there. Wouldn't be part of the output anyway. It was just really the hello world. But you can see exactly what printed out on the terminal, or in my run output. Yeah, and I didn't even need to have return there. Now I am going to be okay if you leave it out. I do not like to leave it out for the same reason that I like to color within the lines, and I am generally considered a rule follower. I told you this function was going to return an integer, and the idea of me telling you it's going to return an integer and then not having a return line with an integer, I'm not OCD. I've never been diagnosed. I really don't feel that I am. I feel like I have, I'm mildly, there might be some traits. I just don't like that. So you do what you want to do. But as for me in this house, I don't know, whatever. I'm going to return the 0 because I said I was going to. By the way, that is the only function where you can leave out a return if you said that you were going to return something. If you have a function you don't want to return anything, you can actually say you want it to return void. And here, by the way, notice I have to put void. I can't just put space, because for reasons we won't get into right now, if you're the compiler and you're trying to parse this, that becomes really hard, because I think that you're trying to return main in this function, and main is not a type that I know, and then this is just all going to confuse me afterwards. The other thing is, in most implementations, and if you chose to go the Visual Studio route, it is not true in Visual Studio for Microsoft. Microsoft will actually allow you to have main return void. I don't know why. That's not part of the language, like the standard, but they do allow it. I think they probably just fix it on the back end for you. But you can do it there, but don't. This is the way it's supposed to work. Main is supposed to return int. That's what everybody expects. If you want to just do it so you can leave out the line, just leave out the line. That's fine. I think that's been doable since, what, C++ 17? Something like that? Anyway, may have been C++ 14. Don't really care. Point being, put the return 0 in because it's the right thing to do. It's like returning your shopping cart. Now, let's get a little fancier here. I said that this was a string, and I sent a bunch of characters. Notice if I change the characters here, right, and I run it again, I got rid of that comma. Now I'm speaking bad English. speaking bad. I'm speaking English poorly. Writing English poorly? I'm speaking. Whatever, it's fine. Hello world appears there. By the way, is world supposed to be capitalized? I don't know. Not in English class. It's fine. So hello world is there and doesn't have the comma. I could change other stuff here. I could also put in some random characters. For instance, what if I didn't put a space, but I put \t? Well, that's something special called an escape sequence. That one happens to represent a tab. And so you can see there are like 5 spaces in between hello and world, even though there are no spaces there. This thing got converted into a different character. And those characters are called escape sequences. They're called escape sequences because they start with /. So as soon as the computer sees /, it's going to look for one of its escape sequences, a series of letters afterwards that would actually do something, and it will interpret it as that character and then continue on with the string. So the escape sequence is kind of important. There are actually a few different ones, and let me just pull up a quick thing here to show you some of the more common ones. \n does a new line, which is the exact same thing as end line. We'll talk about that one in a second. \t we already did for tab. \quote mark makes a lot of sense. How can I type a quote mark into a string if a quote mark ends the string? I couldn't do it. The only way I can do it is by backslashing those quote marks so that I'm telling the computer, this is not me ending the string, this is me wanting you to put a quotation mark into my string. Now that also means that if I have a backslash and the next, how do I get a backslash into my string? Because that's actually really useful, especially for Windows machines. That's part of your path, right? Are backslashes. So how do I get backslashes into my string? The way that you do it is by backslashing your backslash. So you backslash a backslash, and what will appear in the string is just a single backslash, because it's the only way you can do it, given that we now made the backslash something that starts an escape sequence. It's kind of the same thing with the quotation mark. Because it has other meaning to the structure of the string, we have to be able to escape sequence to get it. By the way, because you're on Windows and you might need to have 2 backslashes back to back, how do you get 2 backslashes back to back? You backslash your backslash, then you backslash your backslash. It takes 4 backslashes to get 2. 2 to get 1, 4 to get 2. You can also produce other characters. So Unicode characters, so by default, C++ uses ASCII characters, which is just an old form of encoding characters. You can't produce as many characters, but it was okay. UTF is a way of producing every character you can imagine. Every different language, hiragana, katakana, kanji, and Japanese, Cyrillic and Russian, whatever it is, Korean, all sorts of, Chinese characters, you can produce those using Unicode. It's a much more international, much more flexible thing. It also allows for emoji. So if you wanted to do something like that, you could use \u, and then you have to figure out what the code is for your particular thing that you want to produce. So for instance, \U 000-1F644 is the escape sequence for the emoji with the eye roll. I just looked that up. Whatever Unicode character you wanted, if you wanted to produce it, you could produce it there. But just realize that in most terminals, you're not going to be able to get emojis. That's going to be on a system that's a little bit more capable. But those are what escape sequences are. They are ways of encoding a particular character that you can't normally get on a keyboard. And there's a bunch of other ASCII characters that we use that a lot of them are invisible, but they're helpful for formatting files and things like that. Your average copy of Microsoft Word uses all sorts of invisible characters to create, columns and all sorts of things. So there you go, escape sequences. Now, back to C-line. And so notice, hello world. Notice I could have just done \n here and gotten rid of this bit. Absolutely, totally doable. That's actually just as good, probably better. The only time I really use end line at the end of a line of code is if I'm ending my line with a variable. And I think that's just because it's easier to type ENLD than it is to type \n quote. Maybe? I don't know. Anyway, point being, 50 ways to do anything, right? Do it however you want. Now here's the other thing. Sometimes in code you will see this. Using namespace standard. That is very common in sort of textbook first, first program usage, right? So what does that do? You notice that all this stuff I pulled out of that library, I had to put std : in front of it. And that's because, like, in order to access cout, I need to kind of know where it came from. The reason for that is that you might have code from multiple vendors. Actually, let's talk about it. By the way, this is, you'll notice that there are nerd glasses in the corner. That's because I will not quiz you on this. This is just behind the scenes. Hey, you want me to pull back the curtain a little bit and kind of explain something that you don't really need to know now, but might be helpful in future, and might, just kind of be like planting the seeds for something you'll understand later. We're going to do that a lot in this class, but the idea here is that you might have code from multiple vendors, right? Big companies don't always write all their own code. They use libraries of code from other vendors. They're using different platforms and stuff. And so there can be name collisions between stuff. Now, I would never write code that contained an object called cout, right? That would be, I don't know, my analogies are going to be terrible. It'd be like having a child named Adolf. Like, no, you can't. That's a famous thing, and it's you don't want to do that. You just don't, right? Cout is so common, probably nobody's going to write code for it. But I say that, one of the YouTubers that I often link to in my classes, because he's got great stuff, formerly worked for EA, is Cherno. And so you may have seen his videos already in this class, because I, reference, and I like for people to get multiple voices for stuff. And so Cherno used to work for EA. EA actually wrote their own versions of all the standard libraries. So they did have a cout. And so in that code, in fact, I think he mentions it when he talks about namespaces, like how do you determine whether or not this object that I'm using is part of the standard library or if it's part of the EA library? And the thing you do is you have namespaces, right? Namespaces, honestly, going back to the idea of naming your children, is a lot like having a last name. It tells you what family that person belongs to, right? Like, I suppose so long as you said, Adolf Smith, you might get away with it. But like, you're always going to have to use that kid's last name, right? And that's exactly what you'd have to do here. Here, I need to know, am I using the Duff Corporation version of Resize, or am I using the Acme Company version of Resize, right? Resize is a pretty common name. It very likely could have a name collision, and I need to know which one it came from. And so that's why we have that, what we call membership operator or scope operator. It's just the two colons that say, hey, like, this thing is a part of this namespace, this family, right? So since pretty much everything that would be part of the standard library comes in the std namespace for C++, then you have to put the std : prefix in front of anything you want to use. But what you could do is just say, hey, when I use an object, by default, assume that I'm using the standard namespace. That makes my code look a little cleaner. It's actually probably the less professional way of doing it, because now I've created ambiguity, at least in the case of Resize, right? Or if you worked at EA, I guess cout, right? Like, I don't know what object I'm using here. Am I using the one from this library or the one from this library? I'd have to go all the way to the top of the file to see what the using namespace was, to know which one you were assuming by default. But the using directive essentially tells the computer, hey, we're going to use the namespace standard, assume the namespace standard for anything. Now, by the way, that's kind of fine because you can always, when you want to use the other one, actually put on that prefix, whatever the library's name is, : and then that one will use the right one. But I mean, if you're just looking at code, that might not be obvious. And so sometimes we want to write code to be clear to other programmers what we're doing, especially if they have to maintain it later on. So using namespace standard is potentially a little lazy, but it happens to work out okay for beginning programming classes because it makes your code look a little cleaner, and everything we're going to use is part of the standard namespace unless we create our own, right? So it'll be fine. So if you want to put the using namespace standard in there, I'm perfectly okay with that. If you want to put std : in front of all of your items, that's also perfectly fine. Oh, and don't worry about that, that's fine. Where you place it, if you place it inside a function, then it will only be for that function. We'll talk about scope another day. The slightly less lazy way of doing this is to actually list the things you want to use. So you can actually say using standard cout. Now, whenever I use cout, it will know that I want the standard version of cout, right? It's a little bit more, it's a little bit less ambiguous. You know what it is what you're looking at, right? Because it's just for those particular objects. But even then, it kind of has the same problem, and you can just use using namespace standard. It's fine. Now, back to our thing here. So because I have using namespace standard, I don't have to have this std in front of my code. In fact, I can get rid of all the stds from my code, and I know you're juvenile, you're laughing. It's just the way they abbreviated standard. I don't know why, and they're also called STIs now, so it's not even a funny joke. Anyway, but here I have now my final version of our first program. And you kind of know what all the parts are and what they do. This includes the IOStream library so that I can use objects and functions from that library. This just makes it so that you understand whenever I use one of those objects or functions, we are going to assume that I'm using the standard namespace for all of them. So I don't have to put the std : in front of everything. This is sort of the header for my main function. It tells me that I'm going to return an integer, that the function is called main, which it has to be because that's the first one that gets called, and it has no input whatsoever. Then within curly braces, whoa, no, don't move anything. Within curly braces, I define the body of my code, and by the way, as a side note, for curly braces, you can also do it this way. I call this sometimes Microsoft style versus standard style. Microsoft, I think, tends to do this, if you look at their code, because they use C#, and C# tends to do it this way. But whatever, I'll do it the standard way. If you like the look of the other way, where the curly braces sort of line up right underneath the header, it's not a bad look. I mean, I get it. That's fine. Do it that way. But I'm okay with just the indentation to know what's inside the main function. That's probably also a good note to have. Notice that this has one indent in. Indentation is really going to show us what is inside of other things. Now, right now, we just have one function and no other branches or loops or anything like that. So it's pretty easy. But as we get more complex, placing these curly braces sort of consistently, indenting consistently, is going to be really, really helpful to maintaining your code, to understanding it, to knowing what goes inside of what. So that is pretty much it. Oh, other than, another thing that we sometimes do is we comment our code. So commenting your code just means I'm going to put some words into my code, some lines that are not going to get compiled. They're actually going to get stripped by the time that compiling happens. But it's in the source code so that my fellow coworkers will know what what this code is supposed to do. It's my way of giving messages to people who are going to come after me, or even to myself 6 months later, because I might not remember. And so here, for instance, very common inside of main to tell other programmers what this function does. Now, you probably don't always do it for main, but you could. So this function, tis function, you'll get used to this over the semester. I'm a terrible typist. This function writes a greeting, let me be more specific, to the user on screen. Done. Now you may notice that now I have introduced the dreaded horizontal scroll. Oh no, I do not like that at all. Horizontal scroll on documents is the worst. So what I'm going to do is I'm going to break this up into 2 different lines. All right, now I've gotten rid of my horizontal scroll. Oh, and CLion was smart enough to do the slashes for me. You've ruined my demo, CLion. You can do multi-line comments by doing */ and then ending with, or sorry, /* and then ending with */. So now you can see everything after those comments are going to be commented, and then these 2 lines will not be commented. I could have a paragraph of many, many lines as long as it starts with */ and ends with, as long as it starts with /* and ends with */, I will be just fine. Or I could do kind of what we did there, and every single line just start with 2 slashes. The 2 slashes, when they're out in code, mean like not inside a string. 2 slashes inside a string, sorry, and those would be 2 backslashes inside a string. These are forward slashes. 2 backslashes inside a string just creates a backslash. These are 2 forward slashes, and that just denotes that it's a thing. I will say that you can also do this automatically in CLion. It'll be command or control plus your forward slash. So this uncommented, and then this commented those 2 lines. So you can highlight code, comment it, which means it won't be compiled. That sometimes is useful as you're trying to figure stuff out. But those are basic ways of commenting code, and it is a good idea to comment your code. It's a great way to really, really upset your coworkers and get stuff thrown at you in the lunchroom if you don't write comments on your code, because people want to know, like, what does this function take? What is it returning? What is it doing? Could you give me some clue so that if I have to try and fix it later, I kind of know what X is. Also, don't name your variables X, but that's another week. Anyway, so there you go. Our first program, I mean, entirely dissected. And hopefully that helps you with your first assignment this week. Have a great day.